There are also all of these informal aspects of a conference where, like, we had a gathering of all of the women at the conference last night, and it was really nice, and I made some new friends. So that's the kind of stuff that you would miss if you weren't in person.
Hello, everyone. I'm very happy to be here today to talk about symbolic calculus for high-performance computing from scratch using C++23. So the talk will be long, and it will be more like a tutorial than class or than like a description of what's going on. It will be a tutorial of how to implement yourself symbolic calculus for your applications. So, to describe the topic of this talk, what physicists and engineers usually play with are equations, okay? So, these equations are fine. We can do plenty of analytical stuff with them. But the problem is that when we need to convert them to numerically solve them in C++, we cannot just type them in C++, and C++ will do what we want. So the question that will set the framework of this talk is whether we could have something like symbolic calculus in C++. And the topic of the talk will be about, of course, mathematical expression and how we can represent them as abstract syntax trees, how we can manipulate these trees, and how we can build these trees to have nice interface for users. So the context of this talk is that back in 2019, with Joël Falcou, we presented a talk entitled ADSL Infinity Wars Mainstreaming Symbolic Computation, where we were talking a lot about symbolic calculus and high-performance computing. The hypothesis for this talk is that since this is part of the scientific computing track, you all know about optimization, performance, parallelism. So this part will be your job. So this talk is not about, and that may be misleading, but it's not about complicated math. It's not about high-performance computing per se, because you all know about it, and to have more information about that, you can see the talk from 2019. And it's not about benchmarks, assembly, and optimization. What it is about, it's a tutorial so that you can build your own symbolic calculus engine fitted to your needs from scratch using C++20 and C++23. So the key idea was taken from the talk of 2019, which was stateless expression templates. Because we used to do expression templates where data and the symbolic calculus were intertwined, and expression templates were stateful. And back in 2019, we had the idea to distinguish between these two things and have, from one side, formulas that are stateless, and the other side, data that is injected into formulas, and both live in their own different world. And that reduces a lot of coupling, and that completely reduces a lot of the complexity that were linked to expression templates. So what changed since the previous talk? So C++20 and C++23 came. So the rough ideas remain the same, but it's possible to have a way nicer interface. And this talk, we will focus on a nice interface and how you can build them. And if you have to remember to recall something from this talk, is that generally, like, for example, when physicists or engineers are given a library, generally they use the abstraction that were in the library and try to fit what they have in their head on the abstraction that the library provides. Here, we will do the complete opposite, which is generally the good thing to do when you want to design domain-specific language, which we will start from what we would like to type, and we will reverse engineer the language to fit that. So what would we like to type? So we'd like to be able to define symbols, like A, omega, T, phi. We'd like to be able to provide a formula, which is, for example, a times sine of omega t plus phi, and then be able to inject data so that it will compute the result for us. Okay. And all this talk will be about how to make that possible and how to make that compile in pure C++ 20 and 23. Okay? And if you want the details of how this performs, how it compiles, you can go back to the C++ 20 CppCon 2019 talk. So the question is how to make that happen. So the key idea is will be something that we call the lambda trick. Okay? So if we start from the syntax, and this is something that I will talk about a lot of time during this talk, is that we will always start from the syntax and see what we can do to make this syntax work. Okay? So if we start from the syntax, A, W, T, and phi should have all unique types. Okay? So the problem is then, how can we produce a different type every time the user types that? So one first approach would be to use macros to make that happen. That would be a terrible idea, because then it's not like it cannot be, you don't have access to it during the compile time process. But is it doable in modern C++, in plain modern C++? So when we play with lambda, for example, if we define A, B, C, and D this way, every time you will get a new type. So if we compare the type of A and A, of course, it will do the same thing. If you compare the type of A and B, these are different things. So same syntax, but different types at each line. So each declaration of lambda introduces a new type. Can we use the thing to make the syntax with symbol work? So what does happen if we mix a default template parameter and inject a lambda there? Okay? So if we write that, what will happen is that when the user will type symbol X, symbol Y, then the same thing will happen and the user will get a different type every time. So the type of X and Y will be different, even though the user has provided the exact same syntax. So this is the starting point of everything, because when we start to have a different type for every variable, then we can do plenty of things with good old template metaprogramming. And this also works with non-type template parameter if we want to avoid to have to type decal type. So auto and just the lambda works the same way. So mixing lambda and default template parameter allow to create uniquely typed symbols. So the one trick to remember during this entire talk is this one. As I said, if you type the following with the provided lambda as a default template parameter, then if the user types symbol A, W, T, and phi, if we compare the type of A and W, these will be two different types. Okay? So to make that a proper type for mathematical symbol, we need a few things. First, we need comparison for symbol types, because if you have formulas with a lot of symbols, it would be nice to be able to reorder terms. The second thing we will need is a binding mechanism so that we can associate symbols and values. The third thing is some kind of constraint so that we can say that this symbol, for example, is a real type, or is an integer, or is a matrix, or whatever. So the next three parts will be about the comparison, the binding, and the constraints. So first, the comparison. So the ideal thing that would be very obvious to do would be to use typeinfo hashcode. Unfortunately, hashcode is still not context explorer in C++23. Even though we would expect that from types, even if the function is supposed to work with polymorphic type, that would be nice. That if we don't have some kind of like polymorphism, to have like a hash code for every type. So it's not possible. So we will use another approach then. So the first thing is that to make it easier to separate the functionality, we will first define a symbol identifier that will qualify every single symbol. So we define this class symbol ID, and we redefine symbols so that for each symbol we provide by default an ID that contains a default lambda. Okay, and this works the same. Okay, this gives the exact same result as previously. So the first approach would be to use a unique integer. So for that, we would need to convert the lambda at compile time to a unique integer, but to my knowledge, it's not possible. So the other approach would be to use a pointer, and that is actually possible to do. So we define the symbol ID the same as before. Inside, we will create something to point to. So we call that singleton. It can be equal to anything. So for the example, I define it as a lambda, but it could be anything. And then we define a static variable that is equal to the address of this lambda. Okay? So the role of the singleton in that is just to have an address to point to that is unique for each symbol ID. And the type of the singleton could be any of instantiable type. So it could be an integer. Okay? The fact that it's a lambda doesn't really matter. The problem that we have then with C++23 is that because symbol ID will be a non-type template parameter for symbol, then we have some restrictions. And the most annoying one for us is that the singleton and address have to be a public interface. So they have to stay public data members to make this interface work. So for now, we do that, but ideally in the future, we would like to be able to hide that as an implementation detail because the user should not be able to do this kind of manipulation. So then we have a unique address defined at compile time for every symbol ID, because every symbol ID will define a new class, and every new class will have a different address for this lambda that I defined as singleton. So then to make them comparable, we can define an operator between two symbols that will compare the address. The only problem is that this is undefined according to C++ standard because pointer comparison for two things that are not in the same array is undefined. But thankfully, we have stdless that allows to do the exact same thing, except this time we don't have this limitation. We can compare two pointers that are coming from two different areas of the program. So to make that better than just stdless, we can use the spaceship operator. So we define operator spaceship returning a strong ordering, and it will take a symbol ID from the left-hand side, a symbol ID from the right-hand side, and then it will compare three-way the two address of the thing. And then, if we use that, then we have an ordering. If we compare the symbol identifiers of symbols, then we can order them by their address. So we are not using, we cannot index them because we do not define any integer, but we can at least define an order on them. And if we want to reorder formulas, that's a very good thing to have. Then the second thing is the binding. So you have a symbol and you want to put a value onto this symbol. So what we would like to, again, we start from the syntax. So it would be nice if the user could just type that. I missed the definition of f. So f is just a formula with AW, t, and phi. So, but the user, it would be nice if the user could just type that thing. So the idea to make that happen is that we will define the operator equal, and we will make it return an object that binds a value to the symbol. So a minimal example would be the following. So we have a symbol binder that takes a symbol and a type. Okay? So the type will be the type of the value. So it will associate the symbol to the value of the type, and it will store the value. okay? And to return the binder, what we want to do is that when the symbol have operator equal being called on it, it will return the symbol binder that will say this symbol is associated to this value. Okay. So in the syntax, you can see that operator equal doesn't modify the symbol type; it returns the symbol binder. Okay, built from that symbol and the value provided. Okay. So if I go back in that formula with the formula f of a, w, t, and phi, the fact that the user will type a equal 5 will return a symbol binder with the left-hand side between a and the right-hand side being 5. Okay, and it will not do anything on a at this moment. Okay. Yeah.
Where value type come from?
So you define value type equals to t. I'm sorry for that. Using a value type equal t. Okay, so if and because the symbol, so here because the symbol binder builds it from the value here, it will deduce the correct type. Okay. So you build the symbol binder here. Here it will be the symbol. Here it will be the value that is the input here. So the parameter, the value type, or maybe it should be t here. Replace value type by t. The t type will be deduced from the type of x, and this will work. If we go back to the old syntax, that means that when you type a equals 5, then it will deduce 5 as double. Okay. Don't hesitate to ask questions during the talk if something is not clear. So, and I will try to repeat the question. There is a limitation on this strategy, is that the current version copies everything, which might be a problem for vector and matrices. If I go back to the previous slide, the value here is stored completely, okay? So that might be a problem. So ideally, what we would like is that if the user provides a reference, then because the binder should not change anything to the reference, it should convert it to a const reference, if it's a L-value reference, and if it's a R-value reference, it should convert it to a type so that it can actually store it inside the data structure. Okay. So how to make that work? So the strategy will be to remove R-value reference on the type and R-value reference only, and then add const to the non-reference type. Okay. So how to do that? So the problem is that the C++ standard only includes remove reference. We don't have two different traits, one to remove L-value reference and one to remove R-value reference. Okay. So we will introduce a new type trait, remove L-value reference, which is defined by default to it will just return the same type if it's not an R-value reference, and if the type provided is an L-value reference, then it will remove the reference. It will remove the reference on it, and only if it's an L-value reference. Okay, and we do the same thing for R-value references. Okay, the only thing that changed between the two is that here we still remove the reference, but we only remove the reference if when it's an R-value reference. So now we have these two type traits. The second thing we need is something that converts the type to a const type. The problem is that if we add const to reference, then it just returns a reference because like when it's a const ref, it's the type inside the reference that is const qualified. So what we would like is a type trait that converts tref to a const tref. So we will introduce this other type trait, requalify as const. So the first thing, it will be a conditional. If it's an L-value reference, then we will first remove the reference and the type, then add const, then put back the L value reference. Okay, no, nothing magic here. Same thing if it's an R value reference. First we remove the reference, we add const, and we add back the R value reference. And then if it's neither an L value reference or an R value reference, we just add const. Okay, and we introduce this variable, this alias template. Thank you. So we can do the same thing on volatile and on CV, even if we will not use them afterwards. So the final syntax for the binder will be the following one. So first we have the symbol binder between a symbol and class T. So the symbol type is symbol, the value type is the type of T where we removed CVREF qualifiers, and we also provide the symbol value. And then we have the constructor, which is a little bit complicated. So the first type is the first parameter is the symbol. The second one is the type that is taken as a value. So we only take the value if it's convertible to, if U ampersand is convertible to T, basically, that we will qualify as const. We define no except if the conversion doesn't call any exception, which should not. And then we just say that the value is the result of X forwarded through the U parameter. Then we provide an accessor, which is just the operator bracket thing. And we define the value as this thing will qualify as const, remove R value reference value. And this means that if you get an L value reference, it will not store the data, it will just have a reference inside. But if it's an R value reference, then it will store the value inside so that you don't lose your data. And then we just provide a deduction guide that will build the symbol binder with the right thing. And the symbol binder, the user should never see it in practice. It will be a purely internal mechanism. And the symbol, we define the symbol so that we have, so the operator equal now takes T ampersand value, and this will do the correct thing to forward the value and store it in the binder if it needs to. Okay? So that now, with that type traits, we have something that is very lightweight and avoid all copies that we had before. And this is all for the binding mechanism. Then we have the constraint. So at first we have this kind of symbols, but in practice there is a lot of operations that depend on the type you provide. For example, when you have matrices, it doesn't commute. When you have, like, depending on the type of mathematical symbols you have, you may be able to do some optimization that may not be possible in other contexts. So it would be very nice to be able to provide this information and to have a syntax like that. So that by default we can provide a symbol without any properties, but we can also say that this symbol should be tied to something that describes a real value. So the motivation, there are several motivations. The first one is first to provide context for users so that they know what their symbol are referring to. Because in some code, if you just have a symbol in a very complex code that have, let's say, tensors, vectors, scalars everywhere, you may not know what this symbol is referring to. Avoid unexpected conversion so that the optimization you make on your formula are perfectly fine. And then, as I said, leverage mathematical knowledge to optimize the formulas. And as I said, the mathematical operation behavior may depend on the mathematical concepts. For example, the commutativity of operation. So the idea is to provide some kind of symbolic concept. Okay, that would be the equivalent, except that it would be provided as a template parameter. So the problem as of C++23 is that concepts cannot be provided as template parameters, because if they could, we would just pass a concept as a template parameter and the code would do all the job. So we need a hack for that. So just as a note, there are some proposals currently, I think, that are proposing to like make concepts like that would allow to put more things into template parameter as template parameters, including concepts and I think variable templates. So typically that's the type of use case where we would need these kind of things. So the first kind of solution to make that work as of C++23 is a lambda-based solution. So the syntax would be the following, it's just a proposal for a syntax. So we would define something by default unconstrained. And the unconstrained thing, so this class would have an operator parenthesis, that would take a type, and depending on the type, would return whether it's okay to take that type or not. So in that case, for something unconstrained, it's always true. But for example, for a real number, by default, we have something that returns false. But if it's a floating point, then the symbol, like if the value is floating point type, then we might consider that this would be okay to take that, to consider that as a real parameter. And then we would modify the syntax of symbol as the following. So by default, the thing would be unconstrained. And so the syntax would be okay-ish here, but below it would not be so fine, because we would have to type that to make the correct thing. And what this would do is that it would control the type that is provided before allowing or not to bind the symbol and the value. Okay. So this thing, for example, if the type is real, then the thing would be false. Then the requires condition would not be valid, and this function would not be provided, and we could not assign such let's say an integer to real number. Okay, and this is as before, it just builds the symbol binder. An alternative approach would be the following. So this time it would be a trait-based solution. So we would have unconstrained just defined this way. Would have real defined this way, and it could be any composition of a floating point of a type traits thing. And the problem is that then the syntax would be the following. So it would complicate the template signature of the symbol thing, because then you have to provide this template thing as a parameter. But the requires clause would be easier to type and nicer. So it depends where you want to put your complexity. So this thing, the problem with that current interface where here it's a template parameter is that currently in C++, C++ is type generic, but it's not kind generic. So template parameter kinds like types, NTTPs, templates cannot be mixed. So an illustration of that is the following that you may never have seen. So let's say we have a meta function, okay, that takes just of level 0 that just take a type as an input. Then what would we do if we would like to pass this meta function to a meta function that would take it as an input? We'll have to type this thing. So meta function of level 1 would take as an input this thing of this signature, okay? Then of level 2, what if we want to pass meta function wrapper 1 to something of level 2? We would need to type something like this. It compiles in C++. Then same thing for level 3, same thing for level 4. Okay? And every time we have to define a new name for the meta function, because C++ doesn't provide kind genericity. And all of that, just so that you see it compiles, all of the things compiles and are perfectly working in C++. So what we would like, ideally, is something that is able to collapse all these things so that you could say, I have a template parameter. It could be an entity P, it could be a concept, it could be a meta function, it could be anything. So a working approach of nicer interface as the current state of C++ 23, but I really hope that at some point we'll be able to put concepts inside template parameter, would be to wrap traits in types. So put the complexity here. So we would have the trait would be wrapped in the outside structure. So here for unconstrained, always it returns the true type. For real, it just inherits from floating point. And then the symbol would look like this. And the only annoying thing here is that we need to type template. But that would work. And the nice thing here is that we can keep we don't have to put the template parameter, and we can keep a type here. So for now, in the current library that we are developing, we are keeping this approach, but we are really looking for something that would allow kind genericity and allow for generic template parameters. So now that we have comparison, binding, and constraint on symbols, we can see what we can do with all of that. So combining all the previous techniques, we would define the symbol this way. So we have a trait by default that is unconstrained, and we have an ID that is defined as the symbol ID of a lambda that is uniquely defined here as a default template parameter. So the symbol defines an ID, and it defines a binding mechanism, which is the exact same I showed on the slide before. Okay, and this provides all the functionality, or most of the functionality we need from symbols. So then the question is, how do we build mathematical formula from symbols? So now that we have symbols, for example, for sigma, for pi, for x, for mu, etc., etc., we would like to be able to build these abstract syntax trees. Okay, where I think that you've all seen these kind of things, where for each operator you have a node, and then you divide your tree for every operation, and this builds you the AST. Okay, so here in this plot, we have different kinds of nodes. We have function nodes in blue and purple with different arities. We have constants in orange, and we have variables in green. So what we called symbols in the first part of this talk are typically the sigma, x, mu, and sigma. So what to do about the other symbols and how to build a mathematical formula for them. So as I said, so if we look at this formula, the question is, what are all the concepts that are related to the manipulation of formulas, and what will we need? So regarding symbols, we have different types of symbols. We have variable symbols. We have constant symbols. So the difference is that variable symbol to compute something, they need to be bound to some value. We have function symbols. And we can also, depending on the math book, it may provide another name for function symbols, which is operator symbols when you have arithmetic operators. Then we have the concept of free and bound variables. So free variables are variables that act as symbolic placeholders, and when we provide a value, then they become bound variable. Okay? So this is the thing for symbols. Then the expression we build from these symbols. So these are the following concepts we often find in math textbooks. So terms is roughly equivalent of the idea of a mathematical object in this expression. So phi, omega, but also omega times t plus phi is also a term. A formula is, with the same analogy, is kind of a mathematical sentence, or a mathematical statement, like f is equal to blah, blah, blah. Then an expression is just a string of symbols. And an equation is an equality between two formulas. And there is a big difference that is, like in code, there is a clear difference because we don't use the same equal symbol. And an equation is when it should return true when there is a solution to that, to that equation. So this is different from a formula, even though we can name it. So we could type like EQ equals to A times blah, 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 equal X. That would be a valid syntax. And we have additional concepts like a subterm, which is a part of a term. We have sub-expression, which are part of expression. The concept of well-formed expression, which is a string of symbols that satisfy the rules of syntax. And the arity, which is the number of subterms a term has, typically unary, binary, ternary, etc. And then, when we have the symbols and the construction, we have the action we can do in this construction. So there is this thing about symbolic rewriting, where there is the thing about binding, so when we attach a value to a symbolic variable. Then we have substitution, when we replace the symbolic variables with their values. And then we have rewriting, when we are replacing subterms by other terms in formula. So the difference between substitution, like with as we use in our library, the difference between substitution and rewriting is that substitution is about values, like real values that you provide, like 5 or 6 or 42. While subterms is like you want to replace, let's say, x by z over y. Okay. So with all these concepts, then if we take this formula example, we could convert it to this abstract. We would like to convert it to this abstract syntax tree with functions, symbols, and constant symbols sometimes. So there are also several ways to build this formula, several representation, depending on how we build the tree, like from which angle we build the tree, because we can do it pre-order, we could do it in order, and we can do it post-order. So depending on the kind of application and the context, we might want to do some operation in pre-order, some other in post-order, etc., etc. So to make that happen in C++, we will start with one simple concept, which is just is symbolic. So we provide a type trait is symbolic, and we define a concept that is just the representation of the type trait. And then for every type that should be considered as symbolic, we will specialize, it will be a customization point where we'll provide a specialization of symbolic that will be equal to true. So for example, a symbol will be considered as symbolic. Okay? And then we will build everything from there. And it will not be that complicated, as you will see. So the last step that is still a little, I would say, a little bit, that use some kind of template metaprogramming is substitution. So what we would like to do, so for this, as of now, at this point of this talk, this example is still not compiling. But what we would like to have is something at this step, the line number 3, we would like to have some substitution happen, okay? We would like to have A replaced by 5, W replaced by 2.5, etc., etc. So we start from the formula. So we would like to build something that is a formula first. So a formula will be built from an expression that will be considered as symbolic. So a formula is just something that takes as an input an expression, and it has an operator parenthesis that will take a list of arguments, and that will build a magic class here, substitution, and that will pass the arguments to the substitution. So that means that in that line, with what we designed before, here we will receive a binder here, a binder here, a binder here, and a binder here. And the substitution will receive the binders and do something with it, and then be passed to an expression, a mathematical expression, okay? So substitution is the tool, the helper that does something with binders. So as I said, a substitution class can be just seen as a pack of binders. So the general structure of the code will be, we will need an index constant to be able to index our binders in our formula. So we just provide this index constant. Then we will have a substitution element. We will just be an indexed binder. Then we will have a substitution base and a substitution. And substitution will take as an input a list of binders. So how does it work? So the first thing is that substitution will receive a list of binders. And what it will do with it is that it will pass it to substitution base and create an index sequence for it. Okay? So that on one side, we have still the binders, and then we'll have an index sequence of 0, 1, 2, etc., etc. Then we just say that it generates the same, like the operator bracket, because we will use it later. And we just have a deduction guide on it, so that it works fine. Then the substitution base. What it will do, and this is the whole trick, is that it will receive a list, an index sequence that will be built from the index sequence for here, and a list of binders. Okay? And what it will do is that it will inherit separately from each element, from each binder, wrapped as a substitution element with an index and the corresponding binder. Okay? So the substitution base is inheriting, for example, if you have a list of 4 binders, the substitution base will inherit from 4 different types. Okay? So these are just helpers. Again, the only thing we make sure that operator bracket is well defined and well inherited to be able to use it. And the constructor constructs every substitution element the class is inheriting from. And then the substitution element. So substitution element is an indexed binder. So we have an index I and we have a binder B. So it provides an index constant, an ID, which is the ID of the current symbol. Yeah.
Sorry, I lost track a little bit what we're trying to achieve, but you're trying to go from a symbol to the actual value.
Yeah.
Wouldn't just a tuple that's going to be basically having a tuple structure where you're indexing on the actual symbol type and to store the actual value, and that just do it?
So it's so the question is why not just use tuple? It's actually a better version of tuple. But you can see that as a tuple. It provides the same mechanism, except the syntax and the speed of compilation is better compared to current C++ tuple. But this is and there is some magic. There is a magic function that is really helpful. So we have the constructor that just takes the binder as an input. And then there is an access provided, an accessor based on the index, and we have an accessor based on the ID. And this is where the magic happens. Actually, I think there is a proposal in standard tuple to provide the same kind of interface at least for the one with the index. But the idea is that you will be able, if you have the substitution thing, you provide your symbol ID, and it will return the value it's associated to. Okay? And the way it works is that, so let's say you have symbol X, symbol Y. You say S is the substitution for X equal 5 and Y equal 2. With the above syntax, this works. Like if you type S of X and the ID, the symbol ID of X, then it will return the value of 5. And the way it works is the following. So the substitution inherits from the substitution base that have all the indexed binders. Then the substitution base inherits from all different substitution elements. And the thing here is that the operator here is different from each binder because each binder has a unique ID type. So basically, in that case, the substitution here inherits two different operator brackets that call the right value. And then we can go from formula to expression. So going back to the syntax of formula, we have our substitution helper, and then we can go finally to the AST. So at this point of the talk, we still need to make that work. And the last step is to actually build mathematical expression. And as you see of like the talk, it's not, now that we have all the tools, it can be done really easily. So the last thing we miss is a constant symbol. So a constant symbol just wraps entity P, and that's it. And we say that it's symbolic. Okay. And then we can finally build expression. So things are not that difficult now that we have all the pieces. So a symbolic expression will be the result of an operator and a list of symbolic terms. Okay? And that's it. There is no inside. There is nothing inside. Just a list. Just an operator with terms. Terms that can themselves be other terms. And we say that a symbolic expression is something symbolic, of course. And then we can define our operators for symbolic thing. So we redefine, we specialized plus for symbolic left-hand side and symbolic right-hand side. And plus doesn't do anything. It just builds a formula where we have a symbolic expression with, so what would be the operator? It would be SED plus of void. So that will work on every possible parameter. And then the LHS and the left-hand side and the right-hand side, which can be terms, which can be symbols, which can be constant symbols. Okay? And we do the same. So we have a one-liner for every possible operation. So it's very simple and easy to define. So we just take, and the only thing that for them to work is that it has to take something that is symbolic. Okay? And if we want to define a custom function, let's say, for example, sign, so we can define a sign symbol. It will just have an operator parenthesis that will forward the argument to stutzin to actually compute the thing. And then we provide the overload for sin for a symbolic argument until it will do the same thing as for the operators before. It will just build a symbolic expression. And at this point, building this formula works. Okay? So we have A, W, T, and phi. So what will happen is that W and T will call the operator multiplies. It will build a symbolic expression. Then it will be plus phi, so it will build a symbolic expression with the left-hand side being the term W times T, and the right-hand side phi. Then we build another thing on top of that, which will be a symbolic expression for sign, and then the multiplication between the two. So at this point of the talk, with just these things and the definition of symbolic expression, that works. So the last thing that remains is to make that happen. But we have our symbolic, we have our substitution tool. So to make that work, we have to modify the symbolic expression and our symbols also. So what it will do is that, so symbolic expression is that we'll have an operator parenthesis, and it will take a substitution, the substitution class, okay? And it will call the operator on the terms, and we will pass the substitution class to the terms, okay? So what this does is that this will descend the formula and pass the substitution class to all the possible terms, okay? And then we modify the symbol type, and we add this overload, so operator parenthesis, and what it will do in this case is that it will look whether, the operator will look whether the substitution has an ID that corresponds to the ID of the current symbol. And if it has this ID, then it will return the value that is corresponding to this ID. And for constant symbol, it's the same interface, except that this time it doesn't care about the symbol ID, it just returns all the time the same value. Okay? And finally, it just works magically. So we have our nice mathematical symbols. We can write this formula, and this will give the correct result. And this is just the beginning, because then we can do like things that are far more interesting regarding to high-performance calculus. But at least now, users have a nice interface. And as library developers, you can like provide all the optimization you want. And for all the people who are like HPC experts, you can do all you want with the formula. So as I said, building the AST once you have all the basic building blocks is really not that complicated. But still a lot of things are missing. So the first thing is partial substitution. So for now, only full substitution works, which means that you have to provide all the parameters, you have to associate every symbol to a value for it to work. What we would like to work is have partial substitution work, which means that if you call, for example, F for A and W, it should generate a new formula by replacing only the parameter A and W, and keep the other as symbols. Then rewriting. So using the same approach as partial substitution, we would like to be able to do rewriting, where if you call, for example, F with X equal of Y over Z, it should generate a new formula where you have replaced X, the symbol X, with two new symbols. Using the same approach by replacing symbols automatically, it would be nice if we could make a simplification based on the, like, for example, computing derivatives or stuff like that, or looking for terms that cancel each other in some environments where it's fine. And the thing is that it's where the fact that we can order the term is very important. It is really for simplification, because you want to be able to uniquely define your formula before you do the simplification. Then you can do symbolic calculus for derivative and integrals based on the fact that you can replace terms by others and generate new formula. And you can do full-blown custom rule-based rewriting, which could look like a syntax where the user would have a template class, would have a mechanism where they would put like one rule, one second rule, one third rule, and the system would like would derive formula and produce new formula based on this set of rules. And if you have that, then basically you have built a full-blown mathematical engine inside C++. And of course, high performance. So as I said, if you want more thing on high performance, you can look at the talk from 2019. But since all the formulas have all the information about the mathematical AST, it's possible to generate different tasks for calculation. For example, let's say in a part of formula you have some large matrix multiplication. You can put that on the GPU. And you can put like some more complicated function on the CPUs, for example. That would work because you have all the information. The only thing that you would need to modify is when you what you do with your substitution operator, or you can define another formula, like a formula engine that would do the modification on your formulas, and many more things. Because once you have this interface, you can do whatever you want. For example, doing some engine to manipulate physical units. So key idea of the talk is that we propose a new approach to expression template, which is stateless expression templates. So formulas are stateless and data is injected afterwards. The key trick we use is the lambda tricks to make the interface nice. So we generate a new type for each declaration. And the summary of the talk, so we have seen several classes. So symbolic is the general concept of anything that goes into a mathematical formula. A symbol is something the tool to declare a symbolic variable. We have symbol ID to be able to uniquely to compare symbols to order symbols. We have symbol binder, and we have symbol constraint to restrain the mathematical types we can put into a symbol. Then we have a constant symbol like pi, symbolic expression, which are just the composition of symbols and operators, a formula, which is something that is a name given to a symbolic expression, and that starts the process of substitution. And the substitution is the utility that replaces symbols, bar their value, and compute the result. And the thing that is the most important of this talk is that design your abstraction from what you would like to type. Because when users, like C++23 starts to be really, really powerful to be able to design many DSLs, many domain-specific language. And when users are provided this kind of interface, like for users who are not C++ experts, it's really nice for them. And as part of my work, I work with a lot of physicists, and with this kind of interface where they don't need to know what's going on in the background, they are really, really happy with how it works because they can just put their ID into code far more easily. And thank you for your attention, and feel free if you have any questions.
Thank you for the wonderful talk. This was very enlightening. I have so many questions, but before I ask a question, I want to remind you, if you're not aware of it, that Section 5 of the standard prohibits the use of leading underscores in identifiers. And the reason that your code compiles, and this is for everyone else as well, the reason that your code compiles with that leading underscore is because the normative text in the standard says that the compiler need not emit a diagnostic. So that's why your code compiles with leading underscores. But be that as it may, remember that mathematical equations are not just relations among numbers. There is the unit that goes with the number. So even in your sine wave equation, that omega has to be represented as radians per second in order for the sine function to take a radian value as a parameter. So my question on units is, wouldn't it be, and I know you guys maybe haven't done this yet, but I hate to pile on future work, but wouldn't it be great if an expression, as you've laid it out here, failed to compile if the user provided incommensurate units, just like that happens in math, right? I don't get an answer in mathematics or in physics if I don't have commensurate units. So what about that?
Thank you very much for your question. That is actually a very good topic, and there is currently a joint effort with Mateusz Pusch, who is back there, we try to build a library for units, but it's very, very complicated. It's in a topic by itself. But ideally, mixing the two would provide an interface that would be really powerful, and we could totally do what you just described and make some expression compile depending on whether your units are valid or not. So regarding to our long-term view, this is really the kind of things we would like to do in the long term.
Okay, thank you.
Hi, I missed the leading underscore, but I'm pretty sure some of them are allowed. Anyways, I had a question. So lambda in unevaluated context, is it 23?
It's 20, I think.
I think usually doesn't compile for me. Maybe it doesn't.
I'm sure it compiles in 13.3. It's 20, right?
Okay.
Yeah.
Cool. Thank you.
Okay, just one more question. Unicode. Whether you like it or not, maybe in your future or may not be. Do you have plans to deal with Unicode representation? I mean, think of the partial derivative character, right? So how do you represent that in ASCII text? right?
So the good thing with NTTPs is that you can build an engine that will convert a string to an IST that would do this kind of thing. So it's complicated to build, and we made some experiment, but it's possible to build it. You would have an NTTP for example, that would sound like mathematical expression in LaTeX. You would put as a template parameter your string, possibly with Unicode symbols, and then it would, on the back of the thing, it would build the IST in the way we described here.
Yeah. Okay.
In the long term, if you can provide to user where they can just provide their formula in LaTeX to C++ code, for physicists, that would be wonderful.
Yeah. Okay.
And with units.
Right. Looks good though. Thank you.
Hey, so first of all, I have to say again, it's a really good kind of didactic example of building something like this. One question, and I did struggle with a similar problem in my past life. Have you looked into the possibility of having kind of a hybrid, compile time versus runtime? I'm just thinking there are actually two aspects. One of them is when it comes to AST manipulation, you might want to do some AST manipulation based on some rules or something that's, it's not available at compile time. And on the other hand, sometimes you might want to create formula and mess with them kind of similarly, kind of offline. And just kind of, And the other point is that actually AST manipulation would probably be a lot more user-friendly if it's actually in a value format rather than in type space.
Yeah. The thing I was saying about the passing strings as NTTPs, ideally, really what we would like to have is some kind of, all the thing about formula simplification and all of that, have something that can take strings and do the operation on that, and at the end generate so that we can do that either at runtime or at compile time as NTTPs, and then at the end of it generate the formula with a nice interface. So for now, what I presented is possible to do it with IST manipulation at compile time, but ideally we would just like to manipulate string formula in string format and be able to do all these things.
Really cool stuff, though.
Thank you for the talk. For the underscores. Leading underscore followed by a capital letter is reserved anywhere, and leading underscores followed by lowercase is only reserved in the global namespace. So your code's fine. Second, the lambda in the template parameter.
Yeah.
If you define a symbol in a header file and you include that header in multiple translation units, it's going to be a different symbol in both files. So that can cause problems with multiple definitions, or if you put functions in headers that take that. So this is going to have to only work in one translation unit, or you might run into some issues with that. But it's a cool trick.
That's correct. The thing is that, so for now we haven't fully used that, but we think that based on the symbol identifier that wraps the lambda, would be able to kind of conflate and not conflate, but track what symbols are mathematically equivalent in different translation units. We hope that we can make that happen.
Well, if you have a function that takes you say you define a symbol A, or you'd use symbol A in a header, and then you instantiate it in two different files. It'll be two different symbol types, even though they're called the same type. So.
Okay.
Great.
Okay, I think I will finish here. Thank you all, and now you can play with equations.